1 gram of this metal costs $27 million. It doesn't exist anywhere in nature, not one atom. Humans had to invent it, atom by atom, on purpose. A speck smaller than a grain of sand can kill you. It fires off millions of neutrons every single second. Only 2 labs on Earth know how to make it. Scientists handle it with robotic arms, never bare hands. It's locked behind lead, water, and armed security. This isn't uranium. This isn't plutonium. This is rarer. Meet Californium, element 98, and the world's most expensive metal. It was born inside a cyclotron in 1950, not a mine. Every gram in existence could fit inside a sugar cube, yet that sugar cube is worth more than a jet. Doctors inject it into tumors to kill cancer cells. Airports have tested it to sniff out hidden explosives. Oil companies drop it into wells a mile underground. Nuclear reactors use it just to switch themselves on. 1 kilogram has never existed, not once, anywhere. The entire global stockpile is smaller than a coin. It takes years just to make a few milligrams. Its radiation doesn't come from splitting, it splits itself. Spontaneous fission. It falls apart without anyone touching it. That's what makes it a neutron factory in your palm. Neutrons pass through lead like it isn't even there. Only water and plastic can actually slow them down. So why would anyone build something this dangerous on purpose? The answer involves cancer wards, gold mines, and Cold War science. By the end, you'll understand why this element terrifies physicists, and why it might also be quietly saving lives today. Let's go inside the strangest element humans ever created. Californium didn't come from digging, it came from bombardment. In 1950, Berkeley scientists smashed curium with alpha particles. Curium itself was already a man-made element, barely known. 4 scientists led the work: Thomson, Street, Ghiorso, and Seaborg. Seaborg had already helped create plutonium during the Manhattan Project. His lab had basically become a factory for new elements. They named it after California, not a person or myth. It was the 6th transuranium element discovered by that team. The original sample contained roughly 5,000 atoms total. You couldn't see it, weigh it, or even really hold it. Detecting it meant counting radioactive decay, atom by atom. This wasn't chemistry with beakers, this was nuclear physics with instruments. Creating one new element took relentless bombardment for hours. Most atoms produced weren't even the isotope they wanted. Californium sits at atomic number 98 on the periodic table. That places it deep in the actinide row, past uranium. Elements this heavy are inherently unstable by nuclear standards. Their nuclei carry too many protons to stay calm. Every isotope of californium is radioactive. There's no safe version. The most famous isotope is californium-252, and it's the workhorse. CF-252 has a half-life of about 2.6 years. That means half of it disappears every 2.5 years. It doesn't fade quietly. It decays through 2 different paths. About 97% of it undergoes ordinary alpha decay. But the remaining 3% does something far stranger. That small fraction splits apart on its own, spontaneously. No neutron has to hit it first, it just breaks. This is called spontaneous fission, and very few elements do it. Most radioactive materials need an external trigger to split. Californium-252 triggers itself again and again, non-stop. Every split releases a burst of high-energy neutrons. Those neutrons carry no electric charge, so shielding is brutal. Lead, which stops gamma rays easily, barely slows a neutron. That single fact changes everything about handling this element. After Berkeley's discovery, Californium stayed a laboratory curiosity for years. Producing usable quantities required something far bigger than a cyclotron. It required a nuclear reactor built specifically for making isotopes. That reactor wouldn't exist for another decade after discovery. Until then, Californium remained one of science's rarest secrets. Fewer people on Earth had touched it than had walked on the moon. Even today, most physicists have never seen a visible sample. The amounts involved are almost always measured in micrograms. A microgram is 1/millionth of a gram, practically invisible. Yet even that speck behaves like a miniature reactor core. The discovery proved something bigger than one new element. It proved humans could engineer matter atom by atom. Californium became a symbol of how far nuclear science had come, from 5,000 atoms in 1952 grams by today. But grams undersells just how insanely hard that jump was. The next chapter of this story happens inside a reactor, and it takes years, not hours, to pull off. Radioactivity isn't one thing, it comes in different flavors. Some elements emit alpha particles, heavy and easily blocked. Some emit beta particles, faster but still stoppable with metal. Californium-252 does something rarer. It emits streams of neutrons. Neutrons have no charge, so they ignore electric shielding completely. They don't bounce off atoms the way charged particles do. Instead, they slam directly into atomic nuclei. They pass through. 1 microgram of CF-252 releases about 2.3 million neutrons per second. Scale that to a full gram, and the number becomes absurd. That's why even lab-scale amounts are treated as extreme hazards. Alongside the neutrons comes intense gamma radiation from the decay. Together, That combination makes CF-252 dangerous in two directions at once. Neutron radiation can make surrounding materials radioactive themselves. This effect is called neutron activation, and it's a real problem. Storage containers near CF-252 can slowly become radioactive too. That's part of why containment design is so specialized. Standard lead-lined boxes, the kind used for X-ray sources, fail here. Lead stops gamma rays but does almost nothing to neutrons. Neutrons need light, hydrogen-rich materials to actually slow down. That's why water, wax, and polyethylene are the real shields. Hydrogen atoms are small enough to absorb a neutron's energy in a collision. Californium storage containers are often built with layers of polyethylene. Some facilities store samples underwater in deep shielded pools. Remote-controlled manipulator arms move samples so no human gets close. Even trained specialists never handle raw californium with their hands. Dosimeters and neutron detectors monitor every centimeter of the workspace. A tiny sample can still deliver a lethal neutron dose quickly. Distance and shielding are the only real defenses against it. Time near the source is also strictly limited. This is why californium research happens in hot cells. Hot cells are sealed chambers with thick walls and remote tools. Workers watch through leaded glass windows, sometimes inches thick. Every movement is done by mechanical hands, guided from outside. It looks less like chemistry and more like bomb disposal. The neutron output also makes californium incredibly useful, ironically. Neutrons can trigger fission in other radioactive materials nearby. That's exactly why it's used to start up nuclear reactors. A tiny CF-252 source can kickstart a reactor's chain reaction. Without it, some reactors would struggle to reach a stable startup. Its neutrons essentially wake up the fuel inside the core. Once the reactor stabilizes, the CF-252 source is often removed. It's treated almost like a spark plug for nuclear power. The same neutrons that start reactors can also detect hidden matter. Neutrons interact differently with explosives, drugs, and metals. That difference lets detectors see what's hidden inside sealed containers. Security researchers tested CF-252 for exactly this kind of scanning. The technology exists, though its use remains limited and specialized. What makes californium remarkable isn't just danger, it's precision danger. Its radiation is intense, but also strangely useful when controlled. Few elements walk that line between weapon level and life-saving. You can't mine californium, you have to grow it, layer by layer. Production starts with plutonium-239, itself already a reactor byproduct. That plutonium gets loaded into a high-flux nuclear reactor. Inside, it's bombarded with neutrons for extended periods of time. Each neutron capture nudges the atom toward a heavier element. Plutonium slowly becomes americium, then curium step by step. Curium then absorbs more neutrons and becomes berkelium. Berkelium absorbs even more neutrons and finally becomes californium. This entire climb takes years of continuous reactor irradiation. It isn't a single reaction, it's a slow nuclear staircase. Most of the target material never makes it to the top. Only a tiny fraction survives long enough to become californium. The rest decays or transforms into other, unwanted isotopes. This is why final yields are measured in milligrams, not grams. Two facilities in the world dominate this entire production chain. One is the high-flux isotope reactor at Oak Ridge, USA. The other is the research institute at Dmitrovgrad, in Russia. Between them, they supply nearly the world's entire californium stock. Oak Ridge's reactor was actually built with isotope production in mind. It runs some of the most intense neutron fluxes on the planet. After irradiation, the material still isn't pure californium yet. It's a tangled mixture of many different actinide elements. Chemists must separate californium from curium, berkelium, and americium. This separation uses specialized chromatography inside heavily shielded hot cells. Every step happens behind thick glass, using remote manipulators only. The chemistry itself is delicate. These elements behave very similarly. Separating near-identical elements is one of the hardest jobs in chemistry. A single production campaign can take well over a year. From plutonium target to purified californium is often a multi-year project. That timeline is a huge reason for its outrageous cost. You're not paying for the metal. You're paying for reactor time. You're paying for scientists' shielding and years of careful chemistry. Global annual production is typically measured in single-digit grams. Compare that to gold, mined by the thousands of tons yearly. That scarcity alone makes californium orders of magnitude rarer than gold. Oak Ridge has historically sold small amounts to research institutions. Buyers include hospitals, universities, and specialized industrial companies. Every shipment requires strict regulatory approval and secure transport. Radioactive material transport rules apply at every single stage. Some orders are measured in micrograms, not full grams at all. Even research labs often work with barely visible amounts. The production process essentially hasn't changed much since the 1960s. It's still slow, still expensive, and still incredibly labor-intensive. New reactor designs could someday speed this process up. For now, patience is baked into every atom of californium. This is part of why global supply stays so limited. Demand exists, especially from medicine and industry, but supply can't scale. It's not a market problem, it's a nuclear physics problem. You simply cannot rush a neutron capture chain reaction. That's the real reason Californium remains so wildly expensive. Its biggest use by far is as a portable neutron source. Unlike a reactor, it needs no power supply or moving parts. It just sits there, constantly emitting neutrons, no switch required. That makes it incredibly useful anywhere electricity isn't reliable. In medicine, CF-252 has been used to treat certain cancers directly. Neutron brachytherapy places a tiny source right inside a tumor. It's been tested against cervical cancer and some brain tumors. Neutrons can damage cancer cells more effectively than standard X-rays. This treatment remains specialized and isn't as common as chemotherapy. In the industry, Californium powers portable moisture and density gauges. Construction crews use these to check soil compaction on site. Farmers have used similar gauges to measure soil moisture directly. Neutrons scatter differently depending on how much water is present. That scattering pattern tells engineers exactly what's underground, instantly. Oil and gas companies use CF-252 in well logging tools. These tools get lowered deep into freshly drilled boreholes. Neutrons help identify oil, water, and gas-bearing rock layers. This data helps companies decide exactly where to drill further. Airports and security researchers explored Californium for explosive detection. Neutron interrogation can reveal chemical signatures inside sealed luggage. The technology works, but cost has limited widespread adoption. Nuclear power plants use CF-252 sources for reactor startup. Every new reactor needs an initial neutron kickstart to activate. Without a strong neutron source, startup can be slow and unpredictable. A tiny Californium sample solves that problem almost instantly. Once the chain reaction stabilizes, the source is often removed. Researchers also use Californium to test radiation detection equipment. It provides a reliable known neutron output for calibration purposes. Universities use small samples to study neutron physics directly. It helps scientists understand fission, decay, and nuclear interactions better. Metal fatigue detection is another surprising application in aviation. Neutron imaging can reveal hairline cracks invisible to normal X-rays. Airplane parts have been scanned this way for hidden stress damage. Gold and silver prospecting has even used neutron activation analysis. Neutrons can trigger detectable signals from precious metal deposits. Archaeologists have used neutron techniques to study ancient artifacts. It lets researchers analyze composition without damaging the object. Each of these uses relies on the exact same core property: Californium's self-triggered neutron emission, constant and remarkably predictable. No batteries, no switches, no maintenance, just physics doing the work. That reliability is precisely why it's worth the extreme cost. For certain jobs, nothing else on Earth does this quite as well. Synthetic alternatives exist, but rarely match its neutron output efficiency. This is the strange irony at Californium's core, really. The same trait that makes it terrifying also makes it valuable. Uncontrolled, it's a serious radiation hazard, no question about that. Controlled, inside shielding, it becomes one of science's sharpest tools. That balance is exactly why it's guarded so carefully worldwide. Let's talk numbers, because the price tag sounds almost fictional. Oak Ridge has historically cited a figure near $27 million per gram. That number made Californium a regular entry in most expensive lists. For comparison, a gram of gold costs around $65. A gram of platinum runs somewhere around $30. Even a gram of pure diamond doesn't come close to this. So why is Californium priced like it belongs on another planet? First, remember the production timeline. Years, not days or weeks. You're paying for continuous reactor operation across that entire span. Reactor time itself is extraordinarily expensive, even before extraction begins. Then add the specialized chemical separation process afterward. That separation demands hot cells, remote robotics, and expert chemists. Every stage requires radiation shielding built for extreme neutron flux. None of this equipment or infrastructure is cheap to build. Only 2 facilities worldwide can even attempt this production chain. Limited supply, combined with immense demand from research, drives price up. Basic economics says scarcity plus necessity equals extraordinary cost. Californium checks both boxes more intensely than almost anything else. Most buyers don't purchase a full gram, they buy micrograms. A microgram-sized order can still cost thousands of dollars. Hospitals and labs typically only need these tiny amounts anyway. Its neutron output is so intense that a little goes far. You don't need much Californium to get a usable neutron source. That efficiency somewhat offsets the shockingly high per-gram price tag. Still, Californium regularly tops lists of the world's costliest substances. It often gets compared, pound for pound, to antimatter estimates. Antimatter remains theoretical at scale. Californium is real and purchasable. That makes Californium arguably the most expensive real material humans produce. Its rarity isn't artificial scarcity like diamonds can sometimes be. This scarcity is genuine. rooted in nuclear physics limitations. You cannot simply build more reactors overnight to increase supply. Regulatory, safety, and engineering hurdles all slow expansion significantly. Every gram that exists represents years of accumulated scientific effort. That's part of why loss or theft would be so serious. Security around Californium storage rivals precious metal vault protocols. Radiation detectors add another layer beyond typical physical security. Tracking each sample's location is standard practice at these facilities. International shipments require strict regulatory documentation and oversight always. Despite the cost, demand hasn't disappeared. It's actually grown. Medical and industrial applications keep interest steady worldwide. Some researchers argue future reactor tech could lower costs eventually. For now, Californium remains locked at the top of rarity charts. It's a strange kind of luxury item, hidden inside lead containers. No one wears it, displays it, or shows it off, though its value lives entirely in what it can do, not how it looks. That's rare for something this expensive, if you think about it. Most costly things are valued for beauty or status alone. Californium's valued purely for raw physics and precision utility. That distinction makes it one of the strangest treasures on Earth. So what have we actually learned about this bizarre element? Californium doesn't occur naturally. Every atom was made by humans. It took a cyclotron in 1950 to prove it could exist. Today it takes a nuclear reactor and years of patience. Its neutron radiation is intense enough to require robotic handling, yet that same radiation saves lives inside cancer treatment rooms. It starts up nuclear reactors before they can run themselves. It scans oil wells a mile beneath our feet. It's helped detect hidden explosives and structural metal fatigue. And it costs more per gram than almost anything on Earth. 2 facilities, a handful of grams a year. Global demand. That combination makes Californium one of science's strangest paradoxes. Dangerous enough to need lead, water, and armed protection. Useful enough that industries still pay millions to access it. It sits quietly at the edge of the periodic table. Most people will go their whole lives never hearing its name, yet it's touched cancer treatment, energy, and even airport security. That's the strange power of elements humans built from scratch. Californium proves science doesn't just discover nature, it sometimes outbuilds it. If this surprised you, chemistry has stranger stories than this. There are elements rarer, deadlier, and even more expensive out there. Some exist for mere seconds before disappearing forever. If you want that story next, you already know what to do. Hit subscribe if elements like this genuinely blow your mind. Drop a comment. Which element should we investigate next time? Was it the price, the danger, or the medicine that surprised you most? Let me know down below. I actually read every comment. Thanks for watching this deep dive into the world's rarest metal. Stick around, because the periodic table has far stranger stories. See you in the next investigation.